So here we're going to look at two springs in parallel. So all that means is that we have two springs kind of supporting a weight or being pulled. For instance, here we've got them supporting a mass. And what's going to happen is that by being in parallel, we need they have the same extensions. We've got a spring here and a spring here. And the idea is we're going to discount the weight of this little rod that's kind of just keeping them connected to this mass. But the idea is that these springs have to extend the same amount. So however much this one extends by, this one also extends by. So that means these springs have the same extension. So what is the relation between the weight of the mass and the extension of the springs? So what do we need to do? We're going to go through and just write down the kind of things we need for these springs, which remember is their spring constant and their extension. And then from that we can work that out. So what have we done here? Well, we've set up our weight, this mass. We've just said that it's got a weight of W. We said that the springs were this was their original natural length, this distance here, and they've extended by a distance of delta L. So they've started at the same length, so they must have extended by the same amount. That was the key feature here. And then this spring 1 has got a spring constant of K1, and this spring 2 has got a spring constant of K2. So with that, we can work out some things. First of all, we need to note that the weight is clearly supported. It's in equilibrium vertically. Therefore, we must have that the weight W is just equal to the force in both the springs. The idea is the tension in the springs is supporting this mass. So first of all, we need to note that this spring is going to have a force in it, F1, and this spring is going to have a force in it, F2, or rather a tension in it, It will have taken a force F1 to extend it to this current length, and it would have taken a force F2 to extend this one to its current length. So we've drawn that up there. So for our equilibrium, our force balance, we must have that W is just equal to F1 plus F2. And that's pretty straightforward. We've just written that down here. Vertical force balance, W is F1 plus F2. And here's why we can use Hooke's law, because we know what F1 is and we know what F2 is by using the formula we had here, that F is K delta L. So we know that using Hooke's law, F1 is just K1 delta L, and F2 is just K2 delta L, because delta L, remember, is the same for both of them because they both extended the same amount. So we can put that into that equation. So we see that W, the weight, is just going to be, again, just the force in the springs, the force that these springs are applying, their resistance to being stretched. So that's going to be F1 plus F2, as we've written there, but that's really just K1 delta L plus K2 delta L, just substituting that in. But here's where we realise that actually we can kind of factor out that delta L because it's the same for both of them, and so see that the force is just K1 plus K2, and then in brackets, delta L. But let's say we were to pretend that, so that first of all tells us that our weight is just equal to the sum of the spring constants times by delta L. But let's pretend this is actually just one spring. So let's imagine instead of having these two springs in parallel, we just had one spring kind of here, and we went through and worked out.
Hey guys, to continue watching this video and unlock hundreds of other super concise and exam board specific A-level physics videos, just click the Snap Revise smiley face. Join me today, and together let's make A-level physics a walk in the park.